Have you ever wondered if there's a true opposite of you out there, not just in taste, but in the very fabric of reality? For every particle of matter, there's an antimatter twin same mass, opposite charge. When they meet, they annihilate in a burst of energy. Yet the universe is made almost entirely of matter. Where did all the antimatter go? Today we'll explore the top 10 mysteries of this explosive, elusive substance. In the very beginning, at the moment of the Big Bang, the universe burst into existence. According to our best understanding, this event should have created equal amounts of matter and antimatter. These are essentially mirror images of each other, identical in every way except for their electric charge. Matter, the stuff that makes up everything we see around us, and antimatter, its elusive counterpart. If matter and antimatter were truly created in equal amounts, then they would have immediately found each other and annihilated in a burst of pure energy, leaving only light, a sea of photons, the fundamental particles of electromagnetic radiation. No atoms, no stars, no planets, and certainly no us. The universe would be a vast empty void devoid of any complex structures. But here we are, a testament to the fact that something went wrong, or, rather, something went differently than expected. Our very existence is proof that the initial symmetry between matter and antimatter was somehow broken. There was an imbalance, a slight advantage given to matter. In the grand scheme of things, for every billion pairs of matter and antimatter particles that annihilated each other, there was one extra matter particle that survived the cosmic purge, a tiny, seemingly insignificant difference. That tiny surplus, that minuscule advantage of matter over antimatter, is what ultimately built everything we see around us: galaxies, stars, planets, and ultimately, life itself. It's the reason we're here to ponder these very questions. But the question remains, why did matter win? What caused this asymmetry in the early universe? Back in 1967, physicist Andrei Sakharov, a pioneer in the field, suggested that the fundamental laws of physics might not treat matter and antimatter in the same way. Perhaps there was a subtle difference in their behavior, a violation of something called CP symmetry, which dictates that the laws of physics should remain the same if you swap a particle with its antiparticle and reflect its spatial coordinates. The standard model of particle physics, our current best description of the fundamental forces in particles, does allow for a small amount of CP violation, but it's simply not enough to account for the vast imbalance we observe in the universe. It falls far short of explaining our existence. This suggests that there's a missing piece to the puzzle, something beyond the standard model that we haven't yet discovered. Perhaps a new fundamental force or a yet undiscovered particle that tipped the scales in favor of matter in the early universe. Solving this mystery, understanding the origin of matter, could ultimately reveal the deepest secrets of the cosmos and explain why anything exists at all. It's a quest to understand our very origins. In the first unimaginably tiny fraction of a second after the Big Bang, the universe was an incredibly hot, dense soup of energy. It was a period of rapid expansion and extreme conditions, far beyond anything we can currently replicate in our laboratories. From this primordial energy, matter and antimatter were continuously being created, popping into existence from the seething quantum foam. These weren't the stable atoms we know today, but rather a chaotic mix of fundamental particles, and almost as quickly as they appeared, they were destroyed in a perfect symmetrical dance of creation and annihilation, converting back into energy. It was a constant cycle of birth and death at the subatomic level. As the universe rapidly expanded and cooled, this delicate balance began to shift ever so slightly. The conditions were changing and the rules of the game were subtly altered. Creation eventually slowed and then effectively stopped as the energy density decreased, but annihilation continued its relentless work. Except for that incredibly small, almost unbelievable 1 in a billion matter surplus. This tiny asymmetry is the reason we are here today. The energy released from the vast majority of annihilations became the cosmic microwave background, a uniform bath of radiation that permeates the entire universe. It's the faint but persistent afterglow of the Big Bang, a testament to the universe's fiery birth. This faint radiation is a fossil record, a snapshot of the universe as it was only a few 100,000 years after its creation. It also serves as a testament of matter's victory, however slim, over antimatter. Without this victory, there would be no galaxies, no stars, no planets, and certainly no life. But the standard model of particle physics, our best current understanding of the universe's building blocks, simply can't explain the original imbalance between matter and antimatter. It predicts that they should have been created in equal amounts, leading to complete annihilation. Physicists are therefore actively searching for answers, exploring new physics beyond the standard model to account for this discrepancy. They're developing and testing new theories, ideas like supersymmetry, which proposes a whole new set of particles, and grand unification, which seeks to unify the fundamental forces of nature, hoping to find experimental evidence that supports these models and sheds light on the mystery of matter's dominance. These searches are conducted at cutting-edge facilities, at places like the Large Hadron Collider, where particles are smashed together at incredibly high energies, recreating the conditions of the early universe. The quest continues, driven by our fundamental desire to understand the universe and our place within it, for the missing ingredient, the key to unlocking the secrets of our existence. The quest continues for the missing ingredient, the subtle asymmetry that made our universe and ultimately us possible. Antimatter isn't just a relic of the Big Bang, it's still created in cosmic collisions. High-energy cosmic rays smash into interstellar gas, producing antiprotons and positrons. Detectors like the Alpha Magnetic Spectrometer on the ISS sift through cosmic rays searching for antimatter. They've found more high-energy positrons than expected, an anomaly. Could this be a sign of dark matter annihilation or something even stranger? By studying these cosmic messengers, we might glimpse the universe's hidden side. Each positron could be a clue to the greatest mysteries in physics. The search is on for their true origin. The universe is a vast and mysterious place filled with wonders we are only beginning to understand. One of the most intriguing questions is, can we build atoms from antimatter? It seems like science fiction, but it's a very real area of research pushing the boundaries of what we know about the fundamental building blocks of reality. Yes, we can create anti-hydrogen. Anti-hydrogen is the antimatter counterpart to regular hydrogen, the simplest and most abundant element in the universe. It's made from an antiproton, which has the same mass as a proton, but a negative charge, and a positron, which is the antimatter version of an electron, carrying a positive charge instead of a negative one, is its simplest form. This combination mirrors the structure of a regular hydrogen atom, but with all the charges reversed. Creating and trapping antihydrogen is incredibly hard. It's a delicate dance with the fundamental forces of nature. The challenge lies in the fact that antimatter and matter are fundamentally incompatible. It annihilates on contact with matter, converting both into energy and a burst of pure energy, following Einstein's famous equation EMC2. This annihilation makes studying antimatter extremely difficult, as it instantly disappears upon touching ordinary matter. To overcome this hurdle, scientists at CERN, the European Organization for Nuclear Research, use sophisticated magnetic traps. These traps exploit the magnetic properties of antihydrogen to confine it within a carefully controlled space. These magnetic fields are used to levitate anti-atoms in a vacuum, preventing them from touching the walls of the container and annihilating. The vacuum is crucial to minimize the presence of any stray matter particles. In 2010, after years of dedicated research and technological advancements, they trapped antihydrogen for minutes, a monumental achievement in the field of antimatter research. This breakthrough opened a new era of research, allowing scientists to study antihydrogen in unprecedented detail and paving the way for groundbreaking experiments. Now, with the ability to create and trap antihydrogen, we can finally begin to compare antihydrogen to hydrogen to see if they behave in exactly the same way. One of the key questions is, do they absorb light the same way? This is tested using spectroscopy, a technique that analyzes the light emitted or absorbed by atoms. Another fundamental question is, do they fall down or up? Does antimatter respond to gravity in the same way as ordinary matter, or does it exhibit anti-gravity? These experiments, though seemingly simple, test the very foundations of physics, challenging our understanding of gravity, electromagnetism, and the nature of reality itself. Any difference, no matter how small, could reveal new laws of nature, revolutionizing our understanding of the universe and opening up entirely new avenues of scientific exploration. The answers to these questions may ultimately explain why our universe is made of matter and not antimatter, solving one of the biggest mysteries in cosmology. The standard model is our rulebook for particles, built on a deep symmetry called CPT. It says every particle has an identical opposite twin, antimatter. So far, experiments confirm this symmetry to astonishing precision. But the standard model can't explain gravity, dark matter, or the matter-antimatter imbalance. Could CPT symmetry be ever so slightly broken? If so, it would revolutionize physics. Experiments at CERN are stress testing this symmetry, comparing anti-hydrogen to hydrogen for any tiny difference. The results could point the way to a new understanding of the universe. Could there be entire galaxies made of antimatter? In theory, anti-galaxies would look just like ours until they met matter, triggering colossal annihilation and floods of gamma rays. Astronomers have searched for these gamma-ray signatures with telescopes like Fermi. So far, no evidence of anti-galaxies nearby. This suggests the matter-antimatter imbalance was set early and everywhere. If anti-galaxies exist, they're far beyond our reach. The universe, it seems, is a lonely victory for matter, but the search continues just in case. Antimatter isn't just cosmic, it's inside you thanks to medical technology. PET scans use positrons, the antimatter twin of electrons, to image the body. A radioactive tracer emits positrons which annihilate with electrons, producing gamma rays. Detectors capture these rays, creating detailed 3D images of metabolic activity. Tumors, for example, light up because they consume more tracer. Antimatter's destructive power becomes a tool for healing. It's a stunning example of fundamental physics saving lives. The universe's strangest substance is part of modern medicine. Antimatter is the most expensive substance ever made. Creating it requires massive particle accelerators and vast energy, just a few atoms at a time. For every million collisions, you might get one antiproton. Storing it is even harder. It annihilates on contact with matter. 1 gram of antihydrogen would cost over $60 trillion, more than most countries' economies. That's why we only make tiny amounts for research. Antimatter's rarity and cost make it a scientific marvel, not a commodity. For now, it's the ultimate luxury of physics. Antimatter is the most energy-dense fuel imaginable, 100% mass converted to energy. A few milligrams could, in theory, power a starship to Mars or beyond. Antimatter rockets would use magnetic fields to direct the energy from annihilation for thrust. But the challenges are huge: production, storage, and shielding from deadly gamma rays. The cost and danger keep antimatter propulsion in the realm of science fiction. Still, it's the gold standard for future space travel. If we ever master it, the stars could be within reach. Until then, it fuels our imagination. The future of antimatter research is bright and full of questions. Experiments at CERN are pushing precision to the limit, searching for cracks in the standard model. Can we spot differences between hydrogen and antihydrogen? Does antimatter fall down or up? Cosmic ray detectors hunt for signs of dark matter annihilation. Each discovery adds a line to the story of antimatter. We're just at the beginning of this cosmic mystery. The answers could reshape our understanding of reality itself. Antimatter is both the universe's perfect mirror and its greatest puzzle. Its mysteries drive science forward, from the Big Bang to life-saving technology. What broke the symmetry? Does antimatter fall up? Where are the missing antiparticles? These questions keep physicists searching and dreaming. What fascinates you most about antimatter? Share your thoughts below. Keep looking up. The universe's secrets are waiting. If you enjoyed this video, don't forget to subscribe, like, and comment below. Your support helps us bring more amazing science stories to you. Join our community of curious minds, and let's keep exploring the wonders of the universe together.